Welcome to a third episode in a series where I make a solar power control system for my house. In this episode, we will take a look at how I monitor the solar power generation and usage. First up, we'll take a quick look at how current is typically measured using a shunt, as well as the related traps and pitfalls. After that, we will take a look at what I've actually put together and how it all works. Actually measuring the current from a shunt is conceptually not so hard to grasp. After all, a shunt is just a resistor with a very small resistance value. If we know the resistance of the shunt and we can measure the voltage across the shunt, then we can simply use the classic V equals IR formula to calculate the current. For this explanation, I will generally refer to a shunt that gives us 75 millivolts of drop at its maximum rated current of 50 amps. Of course, there are various different shunts out there, so plug in the numbers for your shunt as need be. In fact, most of the large shunts out there only actually specify the voltage drop for a given max current. But you can easily calculate the resistance of the shunt by using V equals IR, and for this specific shunt, that worked out to be around about 0.0015 ohms. This value is actually so small that you're going to have a lot of trouble trying to measure that with your typical multimeter. Actually, dividing with all of these small fractional numbers can be a real pain, so we can also change the formula a bit like this, and that allows us to use our simple multiplier constant instead. Now keep that 666.6 repeater value in mind, because as we progress through this video, this value becomes a bit of a reoccurring theme. So let's do a quick example. In the case it was a 25 millivolt drop, we can simply multiply this by the constant to get the current, and in this case that's 16.67 amps. Easy enough, right? But now let's take a look at how we might practically measure this with an actual circuit. First, we need to make this signal a bit bigger and easier to measure. We can do this with an op amp configured in a non-inverting amplifier configuration. Then we can use an ADC to sample that value. In this case, I'm showing a 10-bit ADC, something like you would find inside an old Arduino Uno. We also need to set the gain of our amplifier so that the full scale range of our shunt is matched with the full scale range of our ADC. The formula used to calculate the gain with this non-inverting amplifier is as shown here. And to get the gain factor, we simply divide the 5V ADC full scale range by the shunt's maximum drop of 75 millivolts. And that gives us a gain factor of 66.6 repeater. That number seems familiar, right? Anyway, this gain basically means that for every 10 amps, we will get 1 volt from the amplifier. Next up, let's arbitrarily plug in a 10k value for the R1 resistor. And working through our basic algebra, we can see that we need a 656.7k resistor for R2. But since no such resistor value actually exists, instead I would probably use a 610k resistor in series with a 100k multi-turn pot, and that would allow for fine tuning of the final gain that we need. And with that gain tuned, we can now be confident that the full scale ADC count of 1023 will match to that of the 50 amps of the maximum of the shunt. So in the end, the formula that we would use to calculate the current would look just like this. And for example, if the ADC returned a value of say 268, the calculation returns a current of 13.1 amps. And now for the caveats, because there are some possible issues with this design that you should be aware of. The first is, you need to give consideration to the sample frequency in relation to the frequency of the input signal. In other words, if the current signal is changing at a much higher frequency than you would be sampling at, then the measurement you are making might not be a good representation of the actual current. The second issue is that you need to give consideration to the rail-to-rail capability of the specific op amp that you are using, as this will affect the range of the signal it can output. Say for example, the now ancient LM741 op amp has a terrible rail-to-rail output capacity. Now if I remember correctly, if you're using a simple 0 to 5 volt supply, you're likely only going to see an output swing range of between 1 and 4 volts. It might even be worse than that, but I think it's something like that. This means, regardless of what the formula tells you, the actual output will be capped to be within this swing range. For our current example, that would mean only measurement results above 10 amps and below 40 amps could be considered valid, which is actually pretty terrible when you think about it. Thankfully, there are now newer generation op amps out there, such as the TLV2372, I think, which I bought recently, the output of which can swing pretty closely to the supply rails, under 100 millivolts, I believe. Now to be honest, losing a little bit of range at the top end of the current measurement scale is likely not going to cause you much of a problem. But at the lower end of the scale, if you want to measure those very small currents, even losing 100 millivolts could be a big problem for your application. Simple fact is that even specialized current sense amplifiers suffer this same issue. And I read in one of the datasheets for one of these types of chips is that to overcome this issue, it was generally recommended to use a slightly negative VSS supply rail. Doing that gives the output signal a little bit more headroom on the lower end of the scale, which stops those smaller current values from being cropped off. Honestly, it seems like a bit of a pain to make a negative power supply just to solve this problem, but there's likely no other way around it. Now for the final point, but likely the most important one of the bunch. So this method of current measurement is actually called low side current sensing. Obviously, because the sensing is done below the load, on the low side. But there's an inherent problem with this method. As we discussed, we expect a voltage drop across the shunt relative to the current, right? But this in turn means that the actual ground and the ground as seen by the load are not going to be one and the same thing, right? They're going to have some potential difference between the two, depending on what the load's doing. And of course, we can't just connect these two grounds together at any point, because doing that will short the shunt. And that means there'll be no voltage drop to measure anymore. As you can imagine, managing these separate grounds will be a real pain in the bum to deal with, and presents all sorts of complexities and risks. Basically, in most cases, this low side current sense measuring method is just not practical to use, really. So the way to get around this issue is we have to move the shunt to be actually above the load and connected to the power supply, and that makes the load's ground and actual ground one and the same again. Unsurprisingly, this method of current sensing is known as high side current sensing. And for this part of the discussion, I will set the VCC as being 24 volts, but generally let's just assume that the voltage will shift around a little bit, just like a battery might. In a way, to get the current, the problem is basically as we discussed just before. We just need to get the voltage drop across the shunt, and then we can calculate the current. But unlike before, we can't simply measure that drop with relation to ground. Instead, we need to subtract the voltage at what I have shown here as point V1 from the voltage at what I've shown here as point V2, and then add some gain to this difference so that it matches with our ADC specification. And we can do that easy enough by using an op-amp configured as a differential amplifier, just like I've shown here. After that, we have the ADC, same as before, and as the calculations related to the ADC also remain the same as discussed before, I won't go over that again. And just as with the low side design, we also still need to give consideration to the sample frequency and the rail-to-rail capabilities of the op-amp, so nothing changes with respect to that either. What is different, however, and much more complicated, is the formula we use to figure out what the values of the resistors we need to use for the op-amp are. And you also need to be aware here that to get a constant gain, the R3 and R1 values should be identical pairs, and so should resistors R4 and R2. There's even a way to simplify this formula where we assume both of these pairs are perfectly matched, but I'm intentionally using the complex form here for reasons that will become clearer later. Different to the last formula, instead of calculating a simple gain, this formula gives the resultant differential voltage after a factor of gain has been applied to the input differential. I hope that makes sense. Anyway, let's plug in some numbers and see how we go. So as before, the full scale voltage we want is 5 volts. And as I've set V2 to be 24 volts for now, V1 is going to be 75 millivolts below that and be 23.935 volts. Next up, for the R3 and R1 pair, let's plug in an arbitrary 10k resistor value. Now calculating the R4 and R2 values does look a bit tricky, but all we need to do is keep in mind that they are in fact the same value, so that simplifies things a bit. And this is what we get, a 666,667 ohm resistor value. No, actually, I was too lazy to work out the proper algebra or walk you through it here. Instead, I simply used the goal-seek function in Excel and it spat out this value. I say work smarter, not harder. So let's test these values a bit and make sure it's all working as we would expect. First, we can drop the supply voltage down to 4 volts. And yep, it still gives us the 5 volt result we would expect, even at this lower supply voltage. What about if we reduce the current by 2/3 of full scale, which would be 50 millivolts drop instead of the 75? And as we would hope, this gives us 2/3 of 5 volts, which is 3.33 volts. So we can say that the differential amplifier calculation is working as we would expect, so that's all good. Okay, let me put that back to full scale again for a second. Sadly, however, this is the point where I pull the rug out from under your feet again and show you that there are some serious practical issues with this design. Let me explain. Even though we said that resistor pairs R3, R1 and resistor pairs R4 and R2 would be identically matched, in reality, the typical resistors we use have a tolerance, and it's usually around about 1% at best. Now you're probably thinking, well, that would be good enough, right? But let's see if that's really the case. And we'll keep it simple. We'll just change the R3 value to be right on the edge of a 1% tolerance. So that will be a 9.9 kilo ohm resistor instead of 10k. So we'll redo that same calculation again using the 4 volt supply and that gives us a result of 5.04 volts, or a 0.8% error compared to what we'd expected. It's not so bad, I guess. But now let's double the power supply to 8 volts and see what we get. Even though we haven't changed the current, the output increased to 5.08 volts, and that in turn means that the error has actually doubled to 1.6%. So not only do we have a gain error, the amount of error is not even consistent. So it's not looking good. And when we really start cranking up the power supply to say 24 volts, the story only gets much worse. Now we get 5.24 volts on the output, or a 4.7% error. It's basically unusable. So in conclusion, we can clearly see that with this design, imperfect matching of these resistors results in a non-constant gain error as the supply voltage changes. And we can also see that this non-constant gain error is particularly problematic when you're working at those much higher voltages. In practical terms, there are, however, a couple of ways to deal with this issue. The first is to buy very expensive high precision resistors, and the second is to do what everyone else does and buy purpose-built current sense amplifier ICs, which already have those high precision resistors built in. It's also the cheaper and simplest option, by the way. Now, it's a bit of a mixed bag out there. When you're choosing a current sense amplifier, you need to at least consider a couple of points. For example, you need to consider the supported input voltage range. In other words, the range of voltages that you're likely going to be connecting to your shunt. You need to consider if you need bidirectional current support. You also need to figure out the gain of the amplifier, and this is typically noted in these chips as volt per volt, or VV. And it seems like 50 volts VV or 100 volts VV are pretty common gains out there, but there are many others out there too. The next up is the common mode rejection ratio, or the CMRR. This figure is provided in dB, which is a confusing measurement method for me. Seems the ranges out there vary from about 80 to 120 dB, with the higher value giving a more accurate result. And you can say this value basically indicates how stable the gain error is as the voltage increases, with the common mode referring to the supply voltage on the shunt. So how much it rejects that supply voltage component without causing an error. And I guess we could also expect that with these higher rated CMRR values, means that they're actually using more precise resistor matching inside the chip as well. Now, if you're working with voltages above 14 volts, then I probably would recommend a CMRR of 120 dB at least. And the final point to consider is the lowest possible output value, which is basically an indication of the rail-to-rail capability of the internal op amp. The ranges out there that I've seen seem to vary anything from around about 50 millivolts to about 200 millivolts. Typically, most of these current sense amplifiers will actually support a negative power supply rail, just like an op amp would. And if you do use a negative power supply, then again, that will allow you to swing the output voltage all the way down to that 0 volts. It's here also that I wanted to recommend this great video series on a channel called Robert's Smorgasbord. I actually stumbled over these videos a couple of years back when I did my mini lathe project. I was actually flailing around trying to get an op amp based solution to work, so his video ended up being pretty useful. So now let's take a look at what I implemented for my actual solar controller. I'm currently using an INA282 current sense amplifier configured in the unidirectional sensing mode. For the battery's current measurement, I did actually try using a bidirectional mode, but the results I got in my testing did not quite make sense. So instead, I ended up using 2 ICs on each of the battery's shunts, one for measuring the positive direction of the current and the other for measuring the negative. Anyway, the spec of the INA282 looks pretty good on paper. A 50 VV gain, a minimum CMRR of 120 dB, it's actually specified up to about 140 dB I believe, and a maximum low swing of around about 40 millivolts. It also has a huge supported voltage range of -14 all the way up to 80 volts, which is more than enough to cover what I'm using with my solar battery. With the 50 volt per volt gain, that means that at full scale, the 75 millivolts will be represented as 3.75 volts. It sort of seems a little bit low, but it actually matches well with the particular ADC that I ended up using. Next, I filtered the output of the INA282 with a simple RC network. The frequency response of the INA282 is apparently around about 10 kHz according to the datasheet, so the filter aims to flatten this out a bit to a more manageable 6 Hz or so. In hindsight, filtering on the shunt input side instead of on the output side probably would have been a better way to do this, but for now, this is how I've implemented it. Next up, this signal goes into one of the 4 switched inputs of the ADS1115, a 16-bit ADC that I'm using. I purposely sample at a rate of 10 Hz, and this should hopefully be fast enough not to miss anything given the upstream 6 Hz RC filter. And even though this is actually a 16-bit ADC, it samples in the positive and negative directions. So for my application, where I only provide a positive moving signal, it's basically a 15-bit ADC with a maximum range of 32,767. This ADC is actually pretty cool. It's got a built-in programmable gain amplifier, which allows you to choose from various operational input ranges. In this case, I'm actually using the ×1 range, which sets the full scale voltage between plus and minus 4.096 volts. In our case, we're only using the 0 to 4.096 volts, of course. In any case, this in turn gives us a resolution of around about 0.125 millivolts per sample step. That's pretty tiny, right? That means to reach the 50 amp full scale range, which we know is 3.75 volts, we'll use exactly 30,000 of the available steps. So the calculation for the current would look like this. And for example, if the result was 320 from the ADC, then the current could be calculated as 0.53 amps. Unfortunately, however, I did encounter a number of frustrating issues that I needed to address with my design. The first was that the ADC sample, taken immediately after switching to a different input, often caused a result which was clearly not correct. Now, I suspect the cause is likely something to do with my unbuffered RC filter design, which I'm using right at the input. In any case, I figured out an easy workaround for this, and all I do is simply dispose of the sample result immediately after switching to a given input. It means I'm actually doing 20 samples per input per second, but only using 10 of those samples. In any case, it's not a big problem for this ADC, as it can do up to around about 860 samples per second. The second and more excruciating issue that I suffered was terrible inconsistencies with the game, depending on the bus voltage or what the inverter load was doing or whatever. Sometimes it would just float around everywhere. In fact, this problem ended up being so bad that only 4 of the 20 chips that I had on hand were somewhat usable. And it was a real struggle trying to make sense of this problem. In fact, I spent well over a month trying to solve it. In the end, I put it all down to the fact that I bought a bunch of these chips from AliExpress. And even though these chips are meant to be very precise, I expect the chips that I got were either rejects from original manufacturing or some extremely poor quality China-made clones. I already know by reading other people's posts and information on the internet that there are some chips that you just don't buy from China, and I guess this is definitely one of those cases. So you live and you learn, I guess. Anyway, I already ordered and received some new current sense ICs directly from RS Components, which is obviously a much more trustable supplier, but they were bloody expensive. I think around about $3 each. But what can you do? There's really no other choice. Anyway, I hope it will work as expected when I finally get around to testing them. And the final problem I had is related to measuring small currents. Again, this widely varied by the particular chip that I was testing, with some of them, again, being completely unusable. So the chip quality here is definitely playing some degree of a role in the problem that I was seeing. But honestly, it's not just that. The worst case low-end swing that we should expect from the INA282 is already stated as 40 millivolts in the datasheet, with the best case being around about 15 millivolts. Now 40 millivolts doesn't sound like a lot, right? But what does this mean in terms of a minimum possible measurable current? Well, it just so happens that 40 millivolts divided by 0.125 millivolts gives an ADC result of 320 steps, right? And 320 is what I intentionally showed in my example to demonstrate exactly how bad this issue really is. Put simply, if we don't use a negative supply and we are unlucky enough to get an IC on the worst side of the specified tolerances, then anything under a half an amp is simply not going to be able to measure. So in the end, I was really just not satisfied with the precision of my current measurement implementation. But at some point, I just wasted so much time getting nowhere trying to solve the various problems that I just had to walk away from it. I calibrated what I had the best I could and moved on to completing the rest of the project. Now let's take a look at the bigger picture and how I connected all this stuff together. There are 2 ADS 1115s connected to the same I2C bus. This gives me a total of 8 analog inputs. The first 7 inputs are for the shunts, each with a dedicated RC filter. The 8th input is set up with a voltage divider with a filter cap, and this is used to measure the voltage on the solar battery bus. The INA282s are actually all installed on little daughter boards, and these are directly screwed to the current shunts. It's a similar solution as to what I did for my mini lathe if you've seen that video. This time however, I added IC sockets which made it a little bit easier to swap the ICs in and out. Actually, this proved to be a pretty critical design choice given all the troubles I had with these ICs. So battery number 1, charge and discharge sense ICs are actually installed on the same daughter board and connected to the same shunt. And that's the same arrangement I have for battery number 2 as well. Then we have the inverter output sense shunt, and then 2 charging input shunts. In any case, only 4 of the iron 282s I had on hand were actually somewhat usable. So currently the IC sockets for battery number 2 and the charge input number 2 I just left empty for now, and these sense parts are also disabled in my software. Currently I'm not using those inputs in any case, so no problem for now, but ultimately I will need to fix this. So just a quick look at how I gather all this information together data-wise. For every input, I record 10 samples each second, or in other words, 1 sample every 100 milliseconds, and I try to keep this timing as accurate as possible. Every time I gather a sample, I push it to a 10 long item stack. Then, every second, I create an average value using stacks, and I do this in the same way for both the current sense values and the bus voltage. From that, I can then easily calculate the power in watts simply by multiplying the bus voltage and the current values together. And finally, I use these watt values to create an accumulated value representing the watt seconds value for each of these values that I'm tracking. Of course, when I'm displaying the values on the UI, I actually divide them down and show them as kilowatt hours. And just FYI, I am actually purposely accumulating in watt seconds because the float mathematics in Arduino is totally broken. Actually, I originally did attempt to accumulate in the fractions of kilowatt hours, but the result I got was absolute garbage. So watt seconds accumulation is what I ended up going with. Actually, trying to accurately calculate accumulative power consumption is a whole story in itself. But I won't go into all of the coding details here, but let's just take a look at some of the general concepts. So what we have to work with are the sample points of current watts gathered at each second point. Ideally, we would want to draw a splined curve type line to follow all of those points, and in the end you'd end up with something that looks like this. And then we'd use some tricky and probably way over my head mathematics to calculate the area under that curve, and the resultant area we got should probably give a pretty precise measurement of the power consumption over time. But as I indicated, that level of math is beyond me, or at least I can't be bothered trying to figure it out. So let's go back to our simple points graph again, and let's just make rectangles to fill in those gaps. Now calculating the total area is actually pretty easy. All we need to do is just multiply the width and height of each of these rectangles and add them all together. And since we know the width of each of these triangles is 1 second, the same as our sample frequency, all we actually need to do is just add up all the sample values. It's as easy as that. But when we overlay what we said was our ideal curve, we can see that maybe this method may not actually be so accurate, and that the accuracy level could actually be affected pretty badly depending on the shape of the curve. But honestly, I believe that probably would be good enough, and the level of error we might see likely very incidental. But because I just can't help myself, I thought I might be able to improve on that with a little bit more effort. So let me just explain what I did, and you can be the judge if it's a good idea or a bad idea. So instead of trying to draw that complicated spline curve, I simply draw a straight line between each of the points. And now for each section of time, we only need to sum the rectangle component down here at the bottom and this little triangle bit at the top. That looks like a much easier problem to solve. And the easiest way to do that is to take the 2 samples on either side of this rectangle, add them together, and then divide them by 2. As the updated graph shows, we're now calculating an area which tracks very well with that original spline curve that we made, although it's probably under a little bit in a few places here and there. So this is what I'm currently using now, and it seems to work okay. But to be totally honest, given the way that I'm already averaging those original sample points, I'm not fully convinced that this method is actually more accurate than just simply adding up the samples. Really, to better understand this, I need to properly mathematically model both of these methods, taking into account my original sampling and averaging method, and figure out which is actually closer to the ideal solution. I guess I'll stick that one on my to-do list too. Alright, enough of all this theory, let's get hands-on with the UI and see what I've implemented so far. First, I'll just point out that at the top of the page here, we have the current date time and the current temperature as it's taken from the controller. Below that, we can see the inverter section of the page. There it shows the mode, which would normally be waiting or operating. And as you can see here, it's currently in the operating mode. Next to that, I show the bus voltage. And below that, a duration value showing how long the current mode has been operating for. And just below that, you can also see the specific date and time of when the mode change actually took place. To the right of the bus voltage, we can see the watts being used by the inverter. And just below that, the accumulated watt hours since the last mode was changed. Below all that, we see something similar for all of the other shunts in the system, with watts and accumulated watt hours for each. So we have charge source 1 and 2. We have the battery 1 and 2 charge values. And finally, the battery 1 and 2 usage values. You'll also see below that, there is a link here that allows us to access the historical information. And here we can see the recorded information for the last completed operating period, as well as the last completed waiting period. The record includes start and finish times, as well as the duration of the operation. It also includes the accumulated kilowatt hours for each of the various shunts. And finally, I logged the bus voltage at the point the mode was entered into and when it exited. Looking at the waiting period information, this is pretty much typical of what we would expect, with the charge source showing 1.2 kilowatt hours accumulated and the battery charge also showing that it has charged 1.2 kilowatt hours. And you've got to remember that these measurement paths are completely independent for both of these. So with these values being so close, it gives us pretty good confidence that the measurement system is working well. And the reason why it is exactly 1.2 kilowatt hours is because the system is configured to exit the waiting period once exactly 1.2 kilowatt hours has been accumulated, which is about half the charge for the battery. It also has some sort of a time window limit, so if the charge is not accumulated before 5 PM, then it will actually just carry that accumulated charge over to the next day and try again. The logic behind all that is to try to remove any risk of ping-ponging between the operating and waiting modes. So once the operating mode begins, we can be pretty confident it's going to run for 5 or more hours before actually switching back into that waiting mode. So that should mean that there should never be more than one operating period in any given day. And if we take that 1.2 kilowatt battery charge accumulated in the waiting period and add that to the battery charge accumulated in the operating period, we can see that the sum of this pretty much equals the battery discharge amount seen during the operating period. In fact, I calculated it once before. The recovery rate was around about 97.5% in this system, which is well within spec of what can be expected from a typical LiFePro 4 battery. Unfortunately, the measurement for the inverter output is not so accurate and can actually be off by plus or minus 10%, I think. You should be able to subtract the battery charge value from the charge source value and then add that to the battery usage value, and the resulting total should be very close to the accumulated inverter output value. But in fact, it's always off by a little bit. Actually, I already knew about this problem based on my original calibration test results. One of the 4 working ICs I ended up using was far less accurate than the other 3. So in the end, I decided to stick this one in the inverter slot, and so this is what we're getting. Even so, the value is still close enough to be a useful reference, so for now I think it's good enough. And talking about the sizing of the batteries or the solar panels, based on the data I've seen so far, generally a sunny day generates around about 2.8 kilowatt hours of power. And the load that I operate with generally consumes around about 3.7 kilowatt hours of power per day. This means for around about 7 or 8 hours of the day, usually in the early morning, the system will switch to the grid to get its power. In general, I think for the battery, it seems that the 2.4 kilowatt hours of storage can easily carry over the night, given a typical sunny day of operation. So I think that's looking pretty good. Of course, it's not going to be enough to carry power through a rainy day, but I never intended the system to be able to do that in any case, so that's fine. In any case, given the general daily generation deficit that currently exists, I tried to figure out a way to squeeze one more solar panel onto my roof. And actually right now, just behind me is sitting a brand new 410 watt panel, which I'll eventually get to installing once it cools down a little bit. So once I get that installed, I'm generally pretty confident that I'll be able to cover all of the load for most of the typical days. In total, this should mean I'll be generating and using around about 110 kilowatt hours of power per month, which is not too shabby. By the way, as I mentioned in the first video, the load for this system was originally planned to only be the lights and the ventilations that I use in my house, but this only ended up being about 1.5 kilowatt hours per day. So clearly I'd reached my originally goal for the project, but it was all a little bit underwhelming. So I decided to look for other loads that I could add to the system, and ultimately I decided to add the entire load of my server room, network hardware, home server, surveillance cameras, stuff like that. And after adding that, it created a pretty much constant additional load of about 90 watts. And actually, that works out to be the bulk of the 3.7 kilowatt hours that I was talking about earlier, using around about 2.2 kilowatt hours per day. Anyway, let's go back to the main page and keep going. Down the bottom here, I show the top line information for the battery backup system for the controller. And clicking on the link shows everything I pretty much demonstrated in that last episode. And obviously the final part to demonstrate is the inverter control stuff, which is hidden behind this little link here. But I'll be covering that in the next episode, so you're just going to have to wait for that. Now I've already got planned a heap of improvements with relation to how I'm monitoring the performance of this system. A big one of those is to totally rebuild the current sense arrangement using better quality chips, and likely I'll end up going back to the idea of using a local microcontroller on each of the current sense daughter boards and communicating to the main controller using the I2C bus. It's a little bit like the Iron A219, right, but a DIY version of that. Also, I want to come up with a way to automatically calibrate all of these sensors, because it works out trying to do this manually is a real hassle. Anyway, I have a bunch of ideas here, so I'll likely cover that in a separate video when I eventually get to it. In addition to improving the hardware, I also want to improve the software and add long-term data logging along with generating various graphs. But even without all these changes, just capturing and displaying information as I'm doing right now still provides great insight as to how the system is performing or how I might need to improve some areas. And I've got to say, the web UI is super quick and convenient. It's a bit of a cliche, I guess, but it's been a real game changer for this application. So that's it for now. I do hope you join me in the next episode. So I'll see you then.